Hi everyone, thank you for tuning in to the Accelerate and Streamline HDL Deployment webinar presented by myself, Vukosi Mboweni. About myself, I'm an application engineer at Opti-Num Solutions and I work within the digital engineering team. I attended the University of Pretoria where I obtained my bachelor's degree in electrical engineering, and I'm currently completing my master's degree in electrical engineering at the University of Cape Town. As an application engineer, I support companies with topics that include, but not limited to, wireless communication, C, C++, and HDL code generation, embedded systems, as well as renewable energy. So about MathWorks and Opti-Num and how the two companies are related, we as Opti-Num Solutions are the sole distributors of MathWorks products in Southern Africa. And MathWorks is an American company whose major products include the mathematical computing software MATLAB, as well as Simulink, the MATLAB-based graphical programming environment for modeling. And this is how the two companies are kind of related. At Opti-Num Solutions, we not only distribute MathWorks products, but we also have a team of highly technical people who work on the consulting side of the business to provide solutions in advanced business analytics, financial engineering, smart mining and manufacturing, as well as digital engineering, where I am a part of. In the agenda today, we've already looked at the introduction. We will look at HDL Coder and model-based design. We'll see the importance of code generation, and then I'll provide or show you a demo. And the demo for today is a linear regression implementation on an FPGA. And it will be broken down into two. So I'll demonstrate generating synthesizable HDL code, as well as using the fixed point designer to actually design the fixed point model. HDL Coder and model-based design. HDL Cogen is basically generating synthesizable VHDL or very low code, where synthesizing means that the HDL code is converted into gate-level description of the circuit mapped to the target hardware. And HDL Cogen fits in the implementation stage of our model-based design workflow. And so with model-based design, we start off with our research and system requirements. We then go on to design the model on Simulink and the Simulink product family. Then we can go in and generate code that we can use to deploy on hardware and test our algorithms. When we are satisfied with this, we can deploy onto the real world, integrate with other devices, and actually create a functional product. Great. So HDL Coder supports this hardware. So we have Intel FPGA boards, SoC devices. We have devices from Xilinx, which include the FPGA boards and the RF devices, as well as FPGA and SoC devices from Microchip. Great. So why do we do code generation? Well, you might have algorithms that are sitting on MATLAB, Simulink, or Stateflow that you want to be deployed on hardware and actually create a product. The key objectives you'll be looking at would be quality, cost, performance, time to market, certification, and other key objectives that you might be considering. So you could go with handwritten code, manually coding everything, but then this is not a good option because handwritten code is slow, it is inconsistent, and it is buggy. And so a MATLAB or Simulink coder can generate code for you, code that is generated quickly, it's consistent, and it is code of high quality, thus helping you move from your algorithms to actually having a real live product. So if you are generating code from a model in Simulink, you need to first understand the functional behavior of the model. You need to validate the model. You need to use model checking tools, and you need to use configuration options that affect code generation. And so then you can generate synthesizable code from your model. In this webinar, I will take you through a production-proven path to take a Simulink model through Fixed Point Designer and then through HDL Coder to target an FPGA. Simulink provides an environment where you can describe how the algorithm design will work through a stream of data and simulate it before actually moving on to hardware implementation. So we can take this model through the fixed point tool since we want to generate synthesizable HDL code. And for this, we need to convert a double precision floating point model to a fixed point model to deploy on a hardware device, in this case, an FPGA. Our demonstration will focus on a linear regression implementation on an FPGA. Some background on linear regression. It is a simple technique that is widely used in digital signal processing, and this is the reason I've selected this example. So we have a function y is equals to f of t that we want to best fit a set of samples. So we'll try to find the best values for the coefficients a and b that will minimize the mean squared error. And so for a linear polynomial function, y is equals to a multiplied by n plus b, the mean squared error is given by this equation, which then leads to the following sets of equations, and the coefficients a and b will have to take on the best values to minimize the mean squared error. So the linear regression algorithm I've just described has been modeled in Simulink. And so we'll now move on to Simulink so we can generate synthesizable code for it. Let's go into Simulink. Great. So now we have here our model. So we have a source coming in. If we inspect the source, we see that it's a sine wave added to some random noise, and then we have an output that is labeled F. And then we have our actual algorithm, which is placed inside this purple area. And then we have some scopes and some displays that are connected to the output to help us visualize the output. Great. So what we want to do now is actually prepare this model for HDL code generation. So let us run this first. Great, and then we can right-click and create subsystem from this purple area. So a shortcut for this is Control-G, but I'll just use that instead. And then we see that a subsystem is actually created for us. And the next thing to do now is to move over to MATLAB and use HDL setup to set up this model for HDL code generation. So this is this the Simulink model, so linear regression underscore start, and then we can use HDL setup to set this up for code generation. If I hit enter, we'll see that some changes have been made, and this model has actually been set up so that we can generate HDL code for it. Okay, great. So some things that have been changed, we see the solver has been changed from variable step to a fixed step, because we want to deploy this on actual hardware, and for this we need a fixed step solver. And so we also see that the hardware type has been changed to an ASIC or FPGA. Great, so let's head back to our model, and we can see that it now shows us the data types propagating through the signal lines here. So we see that the input F is now is a double, and we also have a double output coming from our linear regression algorithm. So then we want to convert this model into a fixed point model. So we can add a data type conversion block over here. So I'll just double click and say data type conversion block and select that and add it here. So we want to represent the data range of F in fixed point. So for this, we need to open I'll just run this first. And then we'll open the data inspector. And then we can inspect the signal F. I'll use a cursor to collect my ranges. So basically about 1.1 to negative 1.1 can represent all the data points in the signal. So this can be represented by a single bit. So we can double click the data type conversion block, and where we see output data type, we can use the notation fixed dt, which represent a fixed point data type in MATLAB. And then this should be a signed value because it has negative and positive values. So this is 1. And then because we want to use a function length of 14 plus a single bit, which would represent the integer part of the data, as well as a single signed bit, will give us 16. So that should be 16 here, and then 14 function length. Once this is done, we can hit apply and hit OK, and then we can update the model. I'll use the shortcut Control D, and we see that the double has been converted to a fixed point, but then we still see a double floating point coming out, as an output from the linear regression algorithm. This is not what we want because we have not fully converted the model into fixed point yet. So we can investigate the matter further. Then double click and open the linear regression algorithm. And we can see that the problem is at the accumulator block subsystem. So we can open the accumulator subsystem, and we can see that the adders, because they have this feedback loop coming back into the adders, this is where we get our output of a double floating point. So I would need to manually set the output data types over here to fixed point. But then for this, we need to collect the data ranges again. Well, not again, for this output, which is some F and also some F. So we can log the signal, we can click on it, and then we can select log selected signal, can do the same and log these two signals. We can then run the model, and then we can open our data inspector, and we can inspect or rather collect the data ranges for these two signals. So if I move my cursor to the peak, I can see that for some F, we have the value 49 as a max, and then the value minus 49 as a min. And then for some NF, it's 1,206 as a max, and then 1,206 as negative 1,206 as the min. So what word length can represent 49 and 1,206? Well, we can use a MATLAB function next power of 2 to get that word length. So we'll head back to MATLAB, and we can say sum f is equals to next power of 2 of the value 49. And I can hit enter, and the value that can the word length that can represent the value 49 is 6. So since we have a one signed bit plus 6 word length to represent 49, and then a fraction length of 14, this gives us a total word length of 21. Let's do the same thing for sum NF, which is equals to next power of 2 of 1,206. This gives us a value 11. So one signed bit plus 11 plus 14 fraction length gives us 26 word length. Great, let's head back to Simulink. Double click on the first adder, which is sum NF. We'll select signal attributes, and under output data types, we'll say fixed T, one signed bit, 26 word length, and the 14 fraction length. We'll apply this, hit OK, and do the same for the second adder, which is a fixed point data type, signed, 21 word length, 14 fraction length. Hit apply, hit OK. If I Control D, we can see that now our fixed point data type has actually, our fixed point is actually propagated all the way to the output. And then one thing to note is that we have an input of a 16-bit or a 16 word length, but then the output is actually 53 word length. And this is a growth of more than 300%. And this is what happens when we manually convert these data types into fixed point. And then I'll show you a trick, which is what the second part, where we'll look at the fixed point tool to actually convert the model into fixed point. This is where it actually helps. But then it's fine. We'll go ahead and actually generate code for this subsystem. So we'll select the subsystem, we'll right click, and then under HDL code, we can check the subsystem compatibility. If we click that, it will then run its checks and see if this subsystem is currently compatible for HDL code generation. So we should expect to see a report pop up soon. And here we go. We have a report that shows us some errors that we need to fix first before we actually generate code for the subsystem. The first error and the second error are delay blocks. And it says HDL code generation is not supported for the control port. Let's click on the link, and it will take us to the two delay blocks that are not supported for HDL code generation. We can remove this code, these blocks, and actually use delay blocks that are supported for HDL code generation. So the library browser, we can select that, and then under HDL Coder in the folder discrete, we can find the unit delay resettable synchronous block. We can drag it into our workspace, and then we can copy and paste that, and we can complete our signal lines. We need to make sure that all the signals are completed. We don't want hanging signals, loose signals. We just go ahead and attach all of those. Great. So let's look at the second error. So at the enable, actually it says subsystem output port A, and the second one says subsystem output port B must have an initial condition of 0 for HDL code generation when in a subsystem with a trigger, enable, or action port. So we can click on the link, and these are the output ports. A, it says the initial condition should be 0. So we'll select 0 there. We'll apply, hit OK. Second one is output port B. Initial condition should be 0 as well. Apply, hit OK. Go back to the root level. Update the model. Right click. Let's check our compatibility again. And then we should have sorted all our errors. So we don't have any errors at the moment, which means we can proceed and actually generate HDL code for the subsystem. So how do you generate code for this HDL code for the subsystem? Well, we have to go to the apps tab, and we can click on the drop down and select our HDL coder. So mine is currently pinned as a favorite, but you can find it under code generation, HDL coder. We'll select that. And then we need to make sure that the subsystem we're generating code for has actually been pinned here. So fortunately enough, it's been pinned for us here. If I were to unpin it, I would pin whichever subsystem I would like to generate code for. So I'll pin the linear regression algorithm subsystem. And once this is done, we can configure some parameters for this code generation. So we can click on the settings, we can go to settings, and we can see that the configuration parameters pane actually comes up. And then the folder to which we want to generate HDL code for is HDL SRC. We'll leave this this way for now. And then we can choose to see certain reports when HDL code has been generated. So we can choose to see a traceability report. We can generate a model view, model web view, an optimization report, as well as timing reports. So hit apply, hit OK, and then we're ready to generate HDL code for the subsystem. So for this, we can simply click on Generate HDL Code, and then we should have our HDL code being generated, and we can go and inspect it after we're done. And another thing that should come up is our report, because we generated the report as well. And here we go, we have the report. One thing I'm interested in is the high-level resource report, where it shows us that we've used 5 multipliers, 5 subtractors and adders, 5 registers, and all the hardware resources that have been utilized. We can see them here. So this is also the work view that has been generated for us to show us the subsystem that we generated code for. Let's go ahead and close this and go back to MATLAB and inspect the code that has been generated. So this is the folder that has been created. So you can double click on that, and we see that the VHDL code that has been generated is here, and we can inspect it if we like. We can take this code and go deploy it, or we can edit it if we like. So great. So now that we have our code, we would like to test it, right? To test and verify that it works the way we'd like. So we can generate a test bench, which we can use with QuestaSim. So to do this, we can simply just click on Generate Test Bench under Verify. And if we go back to MATLAB and the HDL folder, we see that those test bench files have been generated for us. Great. So let's go ahead and open QuestaSim and verify the code that we've generated. So we'll just go ahead and open QuestaSim. I'll just copy this path, change the directory, and this should be // // // Okay, we've changed the directory. So now let's run this compile file. Say do. Great. So now let's simulate and run our tests. Do. Great. And we can see here that our tests have been completed, or they've all passed. And so we have verified our code. If we would even like to inspect the data propagation, we can do so here. I'll go ahead and close QuestaSim. And so we have successfully generated synthesizable HDL code that we can deploy on an FPGA or an ASIC hardware. Right, so as seen in the previous exercise, when using inheritance rules and manual settings, this can lead to a word length growth, as we saw a 300% word length growth, and it is also time consuming. So we can implement fixed data types using the fixed point tool through an iterative workflow that automates common tasks, such as collecting min and max data ranges during simulations. So we can go ahead and go back to MATLAB. And open Let me clear my workspace. In my command window. And then we can open the very same similar the very same model that we looked at earlier. So this is the same one. We see we still have the source, which is a sine wave and an added random noise. We have our linear regression subsystem here that we want to generate code for. And we can simply just go ahead and use the fixed point tool to generate code for the subsystem, right? Great. So we can go to apps and pull up the drop down, and under code generation, we should find the fixed point tool. Can select that. And then we see that in the welcome page, we have different workflows that we can use to convert our model into fixed point. So we'll use the iterative fixed point conversion for this webinar. So I'll select that and select the system under design, which is the linear regression subsystem. And then we can select our tolerances that we want to charge against. So this is, can set this to 1e minus 6 and the output B like that. So we can prepare the model for code generation. I mean, to be used with the fixed point tool. And then it is currently being prepared. And so all the checks have been completed and everything has passed. So the thing to do now is collect all the data ranges in the model. So we can collect all the data ranges. So we can hit collect ranges. So it is busy collecting all the data ranges as we did initially. So great, we have collected all the data ranges, and we see a histogram of the results shown here, which will be very, very helpful in seeing overflows, representable values, in-range values, as well as underflows, potential underflows. So the next thing to do is to change the settings. So under settings, we can set the safety margin for simulation min and max values to 30%, and then we can set the default word length to 20. Once we are done with this, we can propose the data types by simply clicking on propose data types. And it is busy proposing the data types that we have set over there. So we see a potential errors with the model were detected. Select results marked with red X. So the issue here is within the linear regression model. We can add a data type conversion block here. And we can make sure that the output data type will inherit via backpropagation. Great, let's start the process again. Let's save this model. All right, let's set the absolute tolerances for output A and output B. We'll prepare the model again. So it seems there's an issue in one or more preparation, which is the input and output design ranges. All right, let us go back and save this. Make sure everything is fine. Fix point. Select the system and the design. Set the tolerances. Let's prepare. Okay, great. We have all our checks have been completed at this point, so we can go ahead and collect the data ranges. We can hit click on collecting all the data ranges as we did before, and then we'll input our settings. Propose our data types. Great. So now we see that we have potential underflows here and potential underflows here. But it's fine. We'll still go ahead and apply the data types. So we're applying the data types now, simply just clicking on apply data types, and we'll simulate with embedded types. So we can simulate with embedded types. And then it is simulating the model and applying the data types at this point in time, which we can then compare to the baseline of fixed floating point data types. Right. So as well as business simulating, we can go ahead and compare the results. So the results are pretty interesting. The tolerances for the output A and B have not been met. So which means that we need to redo the workflow. So as I mentioned, it is an iterative workflow where we start again with the setting, and we can increase the word length. I'll take it all the way to 25. And then we can propose the data types again, new data types. And then those are being proposed. And this will allow us to actually see the underflows, potential underflows, or overflows that that we can encounter. It's still proposing the fixed point data types. Great, and it is done. We don't have any underflows or overflows at this point in time. We can apply the data types. So we're applying the proposed data types to our linear regression subsystem. Great, and then now we can simulate with embedded types. So this is simulating at this point in time, and we should be able to compare the results of the new data types to the baseline. Great, can click compare results. And great, all the tolerances have been met. And so we'll stick to the word length of 25. And if we close this, we can go back to our model, and we can see that we have an output fixed point data type of 25 word length, which is much smaller than what we had what we had achieved when we did this process manually. And so once we are done with this, we can repeat the process of using the HDL coder to generate code for the subsystem. And so, ladies and gentlemen, we have reached the end of this presentation. We looked at model-based design. We looked at the importance of code generation. We looked at the demos, the first one actually showed how to generate synthesizable HDL code, as well as the second one, which was to use the fixed point tool to convert a floating point model into a fixed point model. Thank you, everyone. If you have any further questions, feel free to reach out to Opti-Num Solutions by email, or you can call or reach us on our social media platforms. We are available on LinkedIn, Opti-Num Solutions. Thank you. Enjoy the rest of your day. Goodbye.